for observing TIDs using HamSci amateur radio validation and climatology. Diego?
Hello, everyone. Share.
All right, looking good.
Cool. Yeah, so my name is Diego Sanchez. I'm a student, undergraduate student at Essex County College, and I'm currently working with Nathaniel Purcell of the University of Scranton and Gareth Perry of the New Jersey Institute of Technology. And this is our work on traveling ionospheric disturbances using amateur ham radio. So traveling ionospheric disturbances, or TIDs, are quasi-periodic variations of F-region electron density that are often associated with atmospheric gravity waves. Current ham radio observation techniques only allow us to track large-scale traveling ionospheric disturbances, or LSTIDs. LSTIDs typically have wavelengths of over 1,000 kilometers and a periodicity of between 30 to 180 minutes, and are often caused by auroral electrojet enhancement and particle precipitation. The main data sources that we used in this study are the Weak Signal Propagation Reporting Network, or WhisperNet, and the Reverse Beacon Network, or RBN, for the ham radio data. And we also used data from Superdual Auroral Radar Network, or SuperDARN, Madrigal GPS Total Electron Content, NASA Omni data, and Ionosonde FOF2 data from the Boulder and Julius Rue Ionosondes. For those who don't know, Reverse Beacon Network is a network of stations that report on the stations that they hear, and WhisperNet is a group of amateur radio operators that use digital radio modes to probe radio frequency propagation conditions. So here we have a figure demonstrating what happens to an HF radio wave when it attempts to pass the ionosphere. As the ionosphere becomes perturbed, the amount of refraction changes, which causes a change in propagation distance. TIDs cause perceived periodic fading in HF propagation when observed using SuperDARN HF radars and ham radio data. And here we have a TID observations using SuperDARN radars. SuperDARN is our radar network that consists of more than 30 low-power HF radars that look into Earth's upper atmosphere, beginning at mid-latitudes and extending into the polar regions. SuperDARN radars see TIDs as periodic fading in their propagation distance, as shown on the top left corner figure via ray trace simulation. The figure on the right shows SuperDARN beam 13 data from November 3rd, 2017 with a TID signature. And the bottom left figure shows the location of beam 13. So here we have the visualizations of RBN and WhisperNet data sources. Figure A shows geomagnetic activity through the KP index. Figure B shows solar activity taken from both the GOES 13 and 15 satellites. These two figures are used to help identify other factors such as geomagnetic storms or solar flares that could be causing disturbances in our histograms other than from a TID. Figure C and D show ham radio activity from spot data coming from both RBN and WhisperNet over a 24-hour period, with our y-axis being the distance from transmitter to receiver and spot density represented by the color scale on the right. On our left, we also have the total number of spots for this histogram, as well as the percentage of data that comes from RBN and WhisperNet. Last, we have a map showing the spot's location. As you can see, we have marked with red arrows here, a particularly pronounced wave-like structure in our 14 megahertz histogram from November 3rd, 2017, that we suspected could be a LSTID, given the apparent periodicity and how relatively quiet the day was in terms of geomagnetic and solar activity. Since HF refraction is associated with ionospheric density, we can use GPS total electron content data to see if these wave-like structures coincide with total electron content changes in the ionosphere. More red colors represent higher total electron content, while the more blue colors represent less. As propagation rises, we see higher total electron content values lower. So here we have a video of from November 3rd, 2017, from 3 o'clock to 6 o'clock. And you can see as time goes by, and we see on the left the ham radio histogram, as the propagation distance rises, we would actually see bluer colors on the TC map. And then as it comes back down again, we see a rise in total electron content. And again, here for 6 o'clock to 9 o'clock, and you could almost see the wave propagating southward here, which coincides very well with what we're actually seeing on the ham radio histogram. So next we used Ionosonde data as another source to compare our ham radio plots to, specifically the FOF2 data. We tried finding ionosondes that were relatively close to the largest concentration of radio spots. For North America, we used Boulder, and for Europe, we used Julius Rue. FOF2 is the highest frequency sent from the ionosonde that reflects back from the ionosphere. The higher the frequency that is bounced back, the higher the electron densities will be. This means that HF range will be shorter at higher FOF2 values and longer at lower FOF2 values. Here we have a comparison from January 26, 2017. As you can see, the lowest peaks in our ham radio plots coincide with the highest peaks in the Ionosonde plots. And here we have another one for the September 27, 2017 for Europe. So next, to find the monthly distribution of TID activity for the year of 2017, I generated daily ham radio plots for both Europe and the US, and I searched them manually for TID signatures. And as you can see here, the majority of activity that I found was more in the winter months, particularly around December, January, and February. So this is for Europe, and here for the US. There was pronounced rise in activity for the month of June for Europe, and around May for US. Currently don't really know what's causing that spike. We're looking potentially maybe at sporadic E as a potential cause for this, but as of right now, not really sure. And to kind of eliminate ham radio activity changing over the course of the year as a potential source for those results, I went and found the monthly average ham radio spots from RBN and WhisperNet to kind of exclude that as being a factor for those results. And next, we began looking at the possible sources into these observed disturbances. Using the same data from the monthly distribution and NASA Omni data, I found that the average hourly max AE and SIMH values for each TID event, which is 1 hour with an observable disturbance in it. I also found the AE and SIMH values for hours that were very clearly quiet to contrast. And the initial results are showing slightly higher max AE values for the TID events. And this is for the US auroral electrojet activity and for the European. And then next I found the SIMH values. They appear to be lower for the TID events, both for US and for Europe. So the ham radio disturbances, they seem likely to be LSTIDs. They appear coherent across the continental US and Europe. They're consistent with SuperDARN, consistent with GPS, and with both the Boulder and Julius Rue ionosondes. showing that it can be RBN and WhisperNet can be used as a tool for not monitoring LSTIDs day and night. LSTIDs are detectable in RBN and WhisperNet observations when the data has been into 2x25 kilometer bins over the US and Europe. And LSIDs affect the available ham radio communication path lengths. There are, however, much fewer observation capabilities during the night using 14 megahertz. The TID activity was more prominent starting in late fall and ending in early spring. The traffic was not, ham radio traffic was not noticeably influenced by season. And the exact mechanism is still uncertain. But I did initially find enhanced max AE values for TID events and lower SIMH values for the TID events. And future work, I'm currently trying to find or develop an automated detection system for these TIDs. Currently, I would have to go through them manually to find these events. Thank you.
All right, thanks very much, Diego. Any questions? Please jump in. We've got a few minutes before the next presentation.
Tina, I see a question in the question window from James LaBelle. It asks, he asks whether you can try looking with a finer granularity in time to pin down whether a particular part of June is responsible for a peak in activity. He says maybe a particular few days event.
Location or time-wise? I'm sorry.
I assume he means field day.
I think no, time-wise, Diego, time-wise.
Okay, sorry.
And he probably doesn't just mean field day. So he probably is thinking of things like auroral sources or other particular events. So what do you think? Do you think you can, do a distribution of the times in June, like identify which days there was more activity?
Well, I could look into that more, but the, I mean, it wasn't influenced by the actual number of spots.
Right, but we could go back and look at the data again and isolate it and say, we saw more activity, say June 1st through 10th, but not like at the end of June.
Exactly. Yes. Absolutely. Yes.
Yeah.
Sorry, I didn't understand the question at first.
and Jim, I just promoted you to a panelist, so if you wanted to ask any questions in person, you can.
Nathaniel, this is Phil. Can I ask one brief one?
Sure.
So Diego, you used SIMH, and I put in the chat, for example, SIMH is generated on a 1-minute cadence. The DST index, which other people have used a lot, of course, is a little more coarse, 1 hour. Do you think your conclusions are improved or different because you're using such a fine scale index as opposed to, the more coarse 1 hour one when you're trying to sort all this data out?
I mean, it's getting pretty diluted because I'm doing hourly averages.
Okay, I get it. Right. So that, for example, if you had used the DST index, which is every hour, maybe then there wouldn't have been too much of a difference, right?
I don't think it should.
Okay.
I could actually, for future, I'll actually remember this, and I'll try to look into that in the future and kind of test both.
Yeah, it might be something that, for example, if you write this up as a paper, some reviewer would ask about.
Okay.
May I ask a quick question? Is there time? Yeah?
Yep, go for it.
Okay, good. So Diego, I'm curious. It's interesting what you're seeing, and you say that some of these TIDs, they look like they are they're seasonal, right? But they're also correlated with aurora. So my question is, because we have so much more of a dense network in the northern hemisphere compared to the southern hemisphere, do you think there's any conjugacy, or is it the seasonal variations? Let's say, summer in the northern hemisphere compared to winter in the southern hemisphere. Do you think those seasonal variations end up washing out any potential conjugacy you might have that would be induced by, let's say, aurora, the auroral oval being somewhat similar in the southern hemisphere as in the northern hemisphere. The reason why I'm asking, I'll just preface why. The reason why I'm asking is because if I get people that ask me, hey, we're having aurora in the southern hemisphere, I'm having all these ham radio issues. If I see something in the northern hemisphere, do I have a ghost of a chance of correlating that to something that might be going on in the southern hemisphere as well, even on just kind of a touchy-feely basis for these people?
I mean, the main thing that I was finding through the TEC plots were that all these were propagating southward. So, I mean, it kind of goes hand in hand, I think. Anything that's going on in the northern hemisphere will potentially be felt in the southern hemisphere.
I think that's still a bit of an open question, Tamitha.
Yeah.
We certainly haven't looked at southern hemisphere data of this. Again, because this RBN WhisperNet data, the way we can see these TIDs in the amateur radio data, it's very, we need that very high dense amount of data. So we don't really have it, as far as I know, in the southern hemisphere.
Right.
However, I can tell you that in another project that I'm just starting to work on now with a new student, we are looking at conjugacies or asymmetries in TIDs and SuperDARN in both the northern and southern hemisphere. So I have a student right now.
How much?
So
how much do you see? How much of an asymmetry? Yeah, how much do you see in the asymmetry, like based on season, for example, during?
We just started that project. We just started that project like a month ago. So
yeah, currently it's all the data that I'm using is the entirety of the U.S. At the same time. So,
right.
Which is why I can only really see LSTIDs. They'd have to be sufficiently large enough to be moving, a majority of the U.S. In its entirety for any given moment.
Yes, Diego,
but they would also have the largest chance for conjugacy, wouldn't they? Because they are so large scale. That's why I'm kind of excited about this, because we might have the biggest chance of seeing conjugacy in these.
Well, what's nice, what I can tell you, Tamitha, is that this particular one of the events that Diego showed here has a 1-to-1 correspondence with TIDs that I can see in the Blackstone radar. And so it's very plausible to look at structures of the same scale size in the Antarctic SuperDARN radars and draw some sort of a conclusion. So we could investigate that.
Nathaniel, we should add that aside from the data sampling problems, right? Kind of like what Carl and I talked about, that for TID sources that are coming up from the neutral atmosphere, the neutral atmosphere is a different thing than the ionized atmosphere, which, if they're electrodynamically driven, there's a field line coupling the north and the southern hemisphere.
Right.
So, Tamitha, it gets back to that question of how much is being generated from below, how much is being generated from above, and what the balance is. And so I'd say sometimes there's good conjugacy and other times there's not. And AGU meetings have whole sessions on that.
Yeah. I know from...
I may have to attend one.
Yeah, I know at least one paper I've read on this sort of conjugacy. They were looking, you can break the traveling ionospheric disturbances down into the electrified traveling ionospheric disturbances, like those associated with like Perkins instability sort of things, and then those associated with the gravity waves. And I know when they've done the conjugacy studies, they focused on those electrified TIDs for obvious reasons.
Understood. Thanks, guys.
All right. Thank you. We are now up to 3:40, and I noticed there were some questions on the element of there being contests at certain times and convenience.